True Mai from the National Renewable Energy Lab. We're going to wait 1 or 2 more minutes before starting. Thank you for joining. Hi everyone, if you just joined us, we're going to start in a moment. So if you just hang on, we'll start in a bit. All right, welcome everyone to this webinar. This is part of a series of grid integration webinars hosted by the National Renewable Energy Lab. This is True Mai. Today we'll be presenting some work that we've done recently looking at wind curtailment and systems operations under a wind vision future. I'm joined today by 2 of my co-authors, Jenny Jorgensen and Greg Brinkman. Jenny will be doing most of the speaking and will be presenting the results with you today after a brief introduction from me. We are all part of the Strategic Energy Analysis Center here at the National Renewable Energy Lab, and we appreciate you joining today. You're all on listen-only mode, but we do have some Q&A planned for the very end. You can enter your questions in the question box, I believe, located in the lower right-hand corner of the GoToMeeting webinar. The overview for the presentation is first, we'll provide some introductory material around project support and other acknowledgements, followed by some background material about the wind vision study. And then I'll turn it over to Jenny, who will be presenting the core results on the methodology and our analysis findings and conclusions. And as I mentioned earlier, we'll have a few minutes for Q&A. But feel free to enter your questions throughout the presentation. Greg Brinkman will be going through the questions and we'll try to address as many of them as we can in the allowed amount of time. So with that, first I'd like to acknowledge that the Wind Energy Technologies Office from the U.S. Department of Energy who supported this work. Certainly appreciate their funding support as well as supporting this larger body of work. We also would like to acknowledge our numerous reviewers who reviewed the report. I'll provide a link to the report itself at the very end, as well as acknowledge a larger number of collaborators at NREL and elsewhere who worked with us along the wind vision study as well as our large grid integration research areas. As I mentioned at the beginning, this is a part of the grid integration webinar series. You can see the link there. We'll have the link shown again at the very end, so no need to copy it now, where you will find a recording of this webinar as well as the slide deck and other report and related research activities. Okay, so starting out before we look at the core analytics results from this particular study, I did want to provide some background on the DOE Wind Vision study for which this project builds upon. The Wind Vision was released in 2015 and it had numerous objectives and purposes which I won't detail here, but it really showed the potential for U.S. wind energy to provide substantial health, environmental, and economic benefits. Analytically, it did this relying on a quote-unquote study scenario from the Wind Vision that looked at a scenario in which wind served 10% of U.S. Electricity demand by 2020, 20% by 2030, and 35% by 2050, as you can see in the chart in the lower right. It did this using the NREL Regional Energy Deployment System model, which is a long-term capacity expansion model to generate these scenarios and assess, again, the health, environmental, and economic impacts of this level of wind deployment. This wind vision study also had some key findings that I'll outline on this slide. First is that it found that with more than 1/3, in fact 35% of U.S. electricity demand supplied by wind, it could support wind capacity additions consistent with the recent past and ultimately leading to new manufacturing and wind turbine demands from other sources like for repowering. It also assessed the electric system impacts, including the grid integration, the wind integration, and transmission challenges associated with this high level of deployment, and found that those integration and transmission challenges are perceived to be manageable. In this particular study, we will be looking at that issue in greater detail, as Jenny will explain. It also looked at some of the costs and benefits and impacts associated with those scenarios. In the lower right, you can see both the impacts to electricity consumers as well as environmental impacts associated with air pollution and greenhouse gas emissions. To realize some of those benefits and impacts, however, we recognize that it requires the need to adequately integrate the wind that is postulated under this wind vision study scenario. Looking at some of the integration and transmission challenges and findings from the wind vision study in detail here, on the left, although we look at a national scenario with 35% wind in the lower U.S., 48 states, we do recognize from the wind vision that in some regions the penetration levels there can well exceed that 35% level. Focusing on the western U.S., we found in the wind vision that in some regions wind penetration exceeded 45% or even 50%. Related to that, in the wind vision, we found incremental transmission needs are needed to move that wind power located oftentimes in remote locations over to load centers that, at least for the western U.S., are located primarily on the west coast there. And transmission is a key element of that and found in the wind vision analysis to be one of the key options needed to support that wind vision. In this particular analysis, we will be zooming in on these integration and transmission challenges, as I mentioned before, focusing again on the western U.S. only. And with that, here are the 3 primary project objectives that is in our new analysis. First is to apply higher fidelity modeling to assess the operational feasibility of such a wind vision study, or future, in the western U.S. The second is to assess the value of transmission, including to reduce curtailment, reduce generation costs, and emissions under this high wind future. Those first 2 objectives are the topic of discussion for today. A third topic, examining the impact of suboptimal transmission scheduling, we also touched on in our research analysis, although we will not be presenting results on that topic today. And with that, I will turn it over to Jenny Jorgensen.
Thanks, Drew. So first I'm going to go through the modeling methods that we used in this analysis, and then discuss our analytical findings and then conclusions. So, all right, so as Drew mentioned, we set out to assess the operational feasibility of wind vision levels of renewable energy in a high fidelity manner. So to simulate the operation of the electric power system, to really get at those integration issues that Drew alluded to before, we used a commercially available production cost software called Plexos. Our formulation of this software simulates a year chronologically with hourly resolution. It commits and dispatches each generating unit in the geographical footprint in the least cost method based on many inputs, including electricity demand, the operating parameters of each individual generator, as well as the layout and physics of the transmission grid. Not only have we been using Plexos here at NREL for about 6 years, but it's also used by utilities and other institutions for system generation and transmission planning. So we started with a Plexos database as well as underlying system data that has been used extensively in stakeholder-vetted integration studies here at NREL. We used nodal transmission, and we represent anticipated transmission from the year 2030. So from there, we aligned the wind, solar, and load from the Wind Vision central study scenario for the year 2050, which contains 37% wind and 12% solar based on available energy as a proportion of total load. The geographical distribution of that wind is shown on the following slide. Again, True mentioned we're only considering the western half of the U.S. in this analysis, whereas Wind Vision, of course, considered the entire U.S. But with our highly detailed simulations, modeling the entire U.S. with multiple scenarios right now is kind of computationally infeasible. So we stuck with the western U.S., but we do consider both land-based and offshore wind, just as the Wind Vision study did, in a somewhat different geographical distribution due to data availability, but very similar in terms of the geographical distribution. So the table on this slide shows the wind capacity as modeled in each state. The table on the left-hand side shows that the wind capacity is distributed fairly well throughout the western U.S. The map shows kind of a different story. The map shows average penetration of wind compared to total load for each state, as well as the maximum penetration. So that's the highest wind penetration considering every hour compared to load. But what the map really shows is that a lot of the wind is found in areas with low demand, such as Montana, Wyoming, and New Mexico. And this kind of gets at the impetus to motivate our transmission aspect of this study, because it sort of follows that all this wind has to be delivered from where it's generated to where it's needed. So before I move into the results, I'm going to emphasize again that this is our starting scenario, which we're going to be calling the reference scenario from here on out. And it contains these levels of wind, as shown on this slide, from the year 2050, as well as our 2030 levels of transmission from our vetted database. And from there, we do multiple transmission sensitivities. But our reference scenario shows, I think the primary result that we want to show is that we didn't find any reliability concerns when modeling over 37% wind and 12% solar in this transmission system. We found no hours of unmet load or unserved reserves in the reference scenario or any of our sensitivities to the reference scenario. The plot on this page shows the hourly dispatch for 2 days in each of 3 seasons for that reference scenario, which basically depicts how generating resources sum to total demand. The red on top represents extra renewable generation that can't be used to help serve load or curtailment. The curtailment, you can see, is pretty high. It's over 15% annually, and it occurs in all seasons, but especially during the non-summer months when demand is typically lower, but resource availability, particularly for wind, remains high. Curtailment can occur for many reasons. One reason could potentially be insufficient transmission to get that wind from where it's generated to where it's needed. Another reason could be the inability of other generation sources, such as coal, to turn down and accommodate this renewable energy. This slide also notes that most of the curtailment is found in the states, from our map, if you remember, the states with the highest penetration of wind, including Montana, New Mexico, and Wyoming. So in order to tease out the cause of curtailment, we ran 2, and these sensitivities aren't realistic, or they don't kind of represent anything in particular, but they were just, our goal was to identify that underlying cause of curtailment. Our first sensitivity, called the retirement sensitivity, removed all coal generators. Coal plants are typically an inflexible source of baseload energy, which are relatively slow to ramp. Takes a while to shut them down and turn them on. So this first scenario was simply to determine if those generators were responsible for curtailment. The second sensitivity, also unrealistic scenario, removed all transmission constraints from the model. The table on the bottom of the page shows that both of these two sensitivities did reduce annual curtailment, but the retirements case reduced curtailment only marginally to 14.9%, whereas the copper sheet scenario reduced curtailment to 0.5%. So clearly, the results of the copper sheet scenario indicate that transmission is the main driver for curtailment in a reference scenario, but also a completely unrealistic scenario in terms of transmission build-out. So we start with our reference scenario to create a more realistic transmission build-out to analyze the impact of new transmission in this high wind future. So again, if you remember, the reference scenario had no new transmission beyond 2030, but our first transmission build-out scenario, which is shown on the map on this slide, contains 4 new lines that have actually been proposed for the western U.S. This adds a total capacity of around 10 gigawatts and substantially reduces curtailment by about half. So a relatively small amount of transmission can reduce curtailment quite substantially in this case. But as you can see, we still have nearly 8% curtailment. So from there, so starting with this more realistic transmission build-out, we beefed up those lines in our transmission 2 scenario by adding 8 gigawatts more transmission capacity to that existing 10, and reduced curtailment to about 6.2%, shown on the map on top. The bottom map shows the third transmission sensitivity, our most speculative transmission build-out, where we add a gigantic line from the high wind states of Montana and Wyoming directly to the load center of Southern California. So this last transmission scenario adds 3 gigawatts of capacity to total about 22 new gigawatts of capacity, and further reduces curtailment to 4.4%.
Jenny, this is Greg. Can I interrupt you there?
Yes.
So can you speak a little bit about how these particular projects were selected, and whether this represents our thought of what the transmission build-out in the West should look like?
Sure, good question. So I'll go back to our first transmission build-out, and I will emphasize again that these lines have all been proposed for the western U.S. And as you can see, they remove, or they take a lot of the wind from those wind-heavy states to places that could potentially absorb the wind. So this one, we didn't have to do any speculation at all. And the next, when we looked at the results of this run, of the first transmission build-out, we still saw a significant amount of curtailment in Montana, Wyoming, and New Mexico. So for the second transmission scenario, we decided to beef up those lines to see if we could further reduce transmission. And then our third transmission scenario, we're still seeing a bit of curtailment in Montana and Wyoming, as well as low levels of curtailment in Southern California, which is why we added this big line that took the wind directly to where it could be used. Does that answer your question?
Yeah, I think so. So is it fair to say that we sort of did one iteration at a time,
yeah,
and then looked to see where we still had curtailment, where we still had high prices, and then tried to find an existing proposed project that might help alleviate that curtailment?
Yeah,
so like the
correct.
First 4 we came up with, and you can see the first 4 on the map basically are the projects that came from the areas with the highest penetration percentage and went to areas with lower penetration percentages. And then, from there we either beefed up those or, in the example of Path 36, found another outlet for some of that renewable electricity that we were seeing lead to congestion, low prices, and curtailment. So each one and each transmission iteration becomes a little bit more speculative as we sort of run out of projects to add, and we started kind of beefing up projects instead.
Yep, that's a good summary. Yes, so this transmission build-out was very manual and iterative compared to the wind vision one, which we'll talk about a little bit later. So finally, kind of the takeaway of these 3 transmission sensitivities is that curtailment continues to decrease with each transmission build-out scenario. However, we do see diminishing returns after the first transmission scenario. So each incremental amount of transmission helps, but not quite as much as that first 10 gigawatts. Actually, I'm going to talk a little bit now about how our transmission sensitivities compare to the Reed's wind vision scenario. As you recall, the wind vision study was built using Reed's, which is a long-term transmission and generation capacity expansion model, whereas we didn't carefully align our transmission with that. We did it very manually, as we kind of just discussed. However, we do end up with getting fairly similar results to that of the wind vision study from Reed's. As you can see on the last bullet on this slide, our transmission expansion in our third scenario was about 22 gigawatts, which is very comparable to Reed's 23 gigawatts that it added between the years of 2030 and 2050. And we end up with very similar curtailment levels. Our modeled curtailment levels in that scenario were 4.4 versus 3% in that of Reed's. And the graph on this page just illustrates that although we didn't carefully align all sources of generation between the Reed's study and this analysis, we see a very similar breakdown in terms of total generation. So finally, we also, as you can imagine, reducing curtailment enables additional cost savings by avoiding fuel. So this is what we're going to talk about on this slide. The model optimizes total generation cost, which is a sum of the three components: fuel cost, startup and shutdown costs, and variable operating and maintenance costs. Fuel costs are by far the largest portion of that. They make up, in our reference case, about 90% of the total generation cost, with about 5% each from the other two components. Each of our three transmission scenarios see a reduction from that reference generation cost, meaning avoided costs. So in this case, it is being able to take that zero marginal cost energy from previously curtailed wind and solar to displace expensive fossil fuels. In this case, natural gas is the most expensive fossil fuel, so the bulk of the savings from that reference case come from avoided natural gas costs. So you can see in our first transmission scenario, we see over $2 billion of avoided costs on an annual basis, which is pretty substantial. But as I mentioned, since that is dependent on the natural gas price, we do a sensitivity to natural gas prices 25% higher and 25% lower, and we see that the costs are still ranging between $1.8 billion and $2.8 billion per year. And of course, this is just avoided generation costs. The reported costs in that table, as the blue box below say, they do not include the capital costs for creating this scenario, or for, in other words, for the capital costs for the wind or other generators or the transmission to create the scenario, just the avoided costs associated with each transmission build-out. So again, we established that these transmission build-outs provide some value in form of avoided generation costs. And since this transmission 1 scenario is based only on proposed projects, we do have an estimate of the capital cost of each of these projects. Those 4 new lines have a total cost of $10 billion. So based on the savings in our reference case, they suggest a simple payback of 4.4 years in the central scenario. And that's just a simple calculation of dividing the capital cost of $10 billion by the annual savings. And even in the lowest natural gas price case, we still see a simple payback of less than 6 years. However, there's a lot of caveats that go along with that. First of all, the generation cost benefit doesn't include other potential value streams for transmission projects, such as reduced firm generator capacity needs. And also that $10 billion cost, the upfront capital cost, is an estimated cost since those projects don't exist yet. So the actual cost for those projects could be substantially higher. Furthermore, even if the system-wide economic case for transmission is really strong, there are big questions about how the cost and savings for such large projects that span such big geographic scopes would be allocated. And clearly, the further transmission build-outs would yield a higher savings, but would also incur higher capital costs along with that. All right. Finally, I would just like to reiterate the key findings of this analysis. Our primary takeaway reaffirms the conclusion that many integration studies and wind vision of wind vision itself, that effective power system operation can be achieved with high renewable energy penetrations, in this case with wind levels greater than 37%, along with 12% PV. Our high resolution grid modeling confirms some aspects of grid reliability, as I talked about before, no unmet load or unserved reserves. However, it's not a full reliability study, which would have to address dynamic stability and frequency response concerns. Secondly, although these systems may be operable with such high levels of wind and PV, problems can also arise. One of those problems are renewable energy curtailment, which reduces the cost and emissions benefits associated with renewable energy. In our reference case, we observed over 15% annual curtailment, but we did also find that this curtailment can be reduced by about half after including 4 new proposed transmission projects to the west. Curtailment can be further reduced with additional transmission with somewhat diminishing returns. And finally, although our discussion of this analysis today has focused on transmission expansion, we also considered the utilization of transmission assets, which we didn't discuss here in the interest of time. But in our report, we discuss and illustrate that inefficient or inflexible transmission scheduling practices, which could include practices like fixed bilateral contracts or the inability to adjust schedules in real-time operations, can significantly increase cost and curtailment. For more details on those sensitivities, you can check out our report, which is linked to on the next slide. And from there, we are going to take any questions from the audience.
Yeah, so this is Greg. So I just encourage people to keep the questions rolling in as we do this Q&A session. We've got a number of different topics that we wanted to talk about right now, but we'd love for people to keep the questions rolling in. So keep them coming. The first thing I wanted to queue up was a discussion about reliability. Jenny, you mentioned that that there was no unmet reserves and no unmet load in the Plexos modeling. But I do think it's important that we mention that that the Plexos modeling alone doesn't completely address the questions about reliability in a future power system. So while we can see the hourly operations of the power system and we don't see any dropped load, we don't see any dropped reserves, there are a few questions that we haven't completely answered with this work regarding reliability. The model does not include, and we did not on this particular scenario run any dynamic analysis, so that leaves questions about any dynamic questions and also voltage stability questions. So frequency response, things like that, the frequency response to contingency on the grid, and also voltage stability are questions that that can be queued up for future work for sure. Now, in this particular model, in the Plexos modeling, we do enforce the path limits in the western interconnection. So this addresses some of the questions about voltage stability, and you know, for example, the California-Oregon interface, you know, probably has more thermal capacity, but we constrain it based on the WEC path limits, which do consider some voltage stability. But it's certainly possible that by adding so much different generation and wind generation, it's certainly possible that that we could introduce new voltage stability questions. And you know, for further discussion of this, I think we'd like to point people to phase 3 of the Western Wind and Solar Integration Study, which looked at some pretty high penetration scenarios and addressed some questions about, what types of options there might be to deal with issues that could be brought up with renewables in terms of frequency response and voltage stability, and how much benefit you might get from adding active power controls and things like that to the renewable generation, to potentially the wind and the solar. Do you have anything to add to that, Jenny?
No, that sounds about right. I think that you're right to identify that as a venue for, or at least a topic for future research. And a few studies have started working towards that, but it's definitely kind of the direction where we're headed.
Okay, great. Okay, we got a lot of questions rolling in quickly, so I will try. We've got a couple that have been queued up here, but so I will try to kind of go through some of the questions that we've got queued up, and then run MC on the questions that we have rolling in too. Jenny, since we've got a little bit of extra time here, you talked a little bit about how we did this analysis looking at in the operational time frame suboptimal transmission scheduling. Can you speak in a little bit more detail about that particular work? Sure.
So in that scenario, again, we started with our reference case, which in Plexos kind of has the optimal power flow solution. So from there, we took that optimal power solution and added a bit of noise on top of it. So while it's not a perfect way of representing inefficient or imperfect scheduling practices, it at least starts to get the idea of what if you're not actually using your transmission in the optimal way. So we introduced varying amounts of noise on that system. In our most extreme case, we saw that curtailment was doubled when we weren't using transmission in its most optimal way. So I think that the analysis that we did starts to answer the question of, what effects can imperfect operation of the power system have on these high wind scenarios. But that's definitely an area for future research as well.
Okay, great. And then, the next question I wanted to queue up was, future work. What do we have planned in this area, and what do we think, should be done in this area? We've covered a little bit of this on the reliability question, the suboptimal transmission scheduling question. Do you want to go into a little bit more detail about what type of work we'd like to see done in the future?
Sure. Yeah. So we've discussed, more reliability studies to follow from this one, hopefully, and perhaps more looking into suboptimal usage of transmission. Another area for future work could be something that we talked about in our cost-benefit analysis, which is the allocation of benefits and costs associated with these giant transmission projects, because they're very large and complicated. In our cost-benefit analysis, we just acknowledge that we don't make any attempt to sort of dig deeper into that issue. And another thing that we would hope to look at in the future is sort of cooperation between different balancing authorities in the West. In our study, we assume sort of optimal dispatch across West. We do have some friction associated with exchanging power between regions, as was implemented in the TEPC-WEC common case that we used. So there is some frequency or some inefficiencies in dealing with the neighbors, but perhaps maybe less than in real life. But it would be good to sort of understand the inefficiencies that result in not having better coordination between balancing authorities in the West.
Yeah, and so studies like looking at expansion of the footprint of the California ISO, or discussions of a Rocky Mountain RTO, right, and also the energy imbalance market in the West. Would it be fair to say that this work points to the importance of those types of studies?
Yes.
Yeah. Yes. Okay. Great. So we definitely see that in the future, studies about those particular questions are really interesting.
Right.
You brought up another point just a second ago about the cost allocation. You said that that in this cost-benefit analysis, we didn't really look at the cost allocation. It's something we don't always look at in detail at NREL because it's a very detailed market type question. But definitely, I would say it's fair to say that that future work looking at the allocation of the costs of this transmission would be really interesting, as our models really show a sort of a social benefit, and we focused here on production cost and things like that. We can also use our models to look at price, so marginal prices, and that's particularly interesting in regions that have markets, that have market operation and where wholesale customers pay the marginal price, and we can look at those types of things, but the cost allocation is a really challenging one that I think will be interesting to look at in the future. Okay, so we have another question about additional studies focused on other U.S. electricity markets. I would comment here that we've done a couple studies. The most relevant recent study would probably be the Eastern Renewable Generation Integration Study, or the ERGIS study, which looks at the eastern interconnection of the U.S. and Canada and looks at 30% renewable penetration. So it's a little bit lower penetration, but we've got ongoing work looking at higher penetrations in the eastern interconnection. We don't necessarily have a direct corollary to this study planned looking at the wind vision scenarios in particular, although Eric Lance is here. I don't know if you wanted to comment on future work that we have planned in this vein.
No, nothing specific. Certainly nothing focused on the east that would look at the wind vision type scenarios. We're still exploring possible new opportunities in this vein, but nothing specific at this time.
Okay, great. And then we also have a couple questions about the hourly versus sub-hourly questions. So we have done all this work at the hourly time scale. Jenny, do you want to talk a little bit about hourly versus sub-hourly, and particularly how we've addressed some of these questions for the low-carbon grid study in California on that?
Sure. Yes, so all of the sensitivities and the reference scenario that we presented today used hourly profiles for wind, solar, and load, mostly due to computational burden. Since we were really trying to make this a transmission-focused study, we decided to do a very detailed job of modeling the transmission system, which meant that we had to make that hourly simplification for our profiles. But we have done some analysis looking at the effect of a 5-minute wind, solar, and wind and solar profiles compared to hourly profiles, which Greg mentioned, for a California low-carbon grid study that Greg and I were involved with over the past couple of years. And basically, we found that looking at the 5-minute profiles, we did see a small increase in curtailment as well as costs, but the sort of main conclusions of the study remained the same, as in we still didn't see any dropped load or unserved reserves, and the benefits associated with renewable energy were still really similar. So that's definitely, I think, also an area for future work, would be doing even a higher fidelity version of this model where we could look at sub-hourly profiles as well.
Yeah, and I'd like to add to that. We've also done some other analysis looking at comparison between sub-hourly, 5-minute, and hourly dispatch to see which conclusions from an hourly model would hold in terms of sub-hourly, of dispatch that happens at a sub-hourly level, particularly looking at the variability and uncertainty of renewables. And we found that the sub-hourly dispatch tended to be most important on small systems that have fewer resources that can handle the variability and uncertainty, and also in terms of if you're interested in results that are marginal in nature, like locational marginal prices, or anything that's sort of on the increment or on the margins of the looking at small differences and things like that. Whereas questions about overall costs, transmission flows, things like that, sort of bulk power flows, things like that tended to have similar conclusions between the 5-minute and the sub-hourly work. I'm sorry, the 5-minute and the hourly modeling. And so, if we did want to dig into this in more detail in future work to look at prices, ancillary service questions, cost to wholesale consumers, things like that. If we wanted to dig into those questions in more detail, then I think that is where we would probably want to start getting into the 5-minute modeling. Okay, so we have another question about discussing the conclusions for all of West versus the West Coast. It might be worthwhile to pull up one of the maps here of the different transmission studies. But Jenny, do you have any comments on conclusions for the Western interconnection as a whole versus the West Coast? And I have a few thoughts on this one too.
Okay, do you want to start?
Yeah, sure. I can get started. So, I mean, as Jenny's pulling up this, there's a little bit of a lag on this, so it's hard to go back a few slides. But as Jenny pulls up these transmission scenarios, the map of the transmission scenarios here, this one, you can see that in terms of penetration, a lot of the Rocky Mountain states get a high level of penetration. In terms of the actual capacity of wind and solar, that is more evenly distributed throughout the Western interconnection. Now, you know, one interesting caveat here that we didn't model in these scenarios because they're based on the wind vision scenarios is that California, Oregon, and Washington all now have 50% RPSs. And I could be wrong, but I believe that it's not really settled how much, what, or how out-of-state generation can play into those scenarios. And so that might be an interesting question going forward in terms of overall costs, out-of-state resources versus in-state resources, and also in terms of operational questions, you know, looking at in-state resources, particularly, you know, in California, solar is the low-cost in-state resource, whereas wind is likely the low-cost out-of-state resource, and these might become interesting questions. But for the wind vision scenarios in particular, with these high levels of penetration throughout the Rocky Mountain states, a lot of the transmission that was motivated by those builds is east to west type transmission that helps bring that renewable resource that's particularly great in the Rocky Mountain states towards the west, where you have a little bit more load. So it's a little bit of comment there on the WEC overall compared to the West Coast in particular. Okay, we got more questions about the different regions, and I mentioned the URGIS study. I want to also maybe mention here the low carbon grid study that we mentioned briefly in California. I think this fits with both of these questions. We looked at the impacts of getting to 50% carbon reduction by 2030 in California, and looked at the impacts of that, and we modeled the entire Western interconnection, but we really focused on questions in California and how the reduction in carbon in the California grid would be impacted by these renewable penetrations and how the operations. So in a lot of the studies that we've done in the last 5 years, we come to a lot of pretty similar conclusions. In that study, we looked at transmission operation, transmission optimization, transmission flows, and how transmission scheduling is done and what kind of institutional practices there are. And we found some of the same conclusions here, although we used some different scenarios and different portfolio of generation, and a different way of addressing the question. But we still basically came to the same overall conclusions that transmission scheduling is very important and can have an enormous impact on, particularly on curtailment levels and things like that. So, so that's a little bit of extension on the question about other regions. All right, True, could you speak a little bit more to some of the future work that we may be doing in terms of storage and?
Yeah, thanks, Greg. Yeah, there were a few questions about storage and a few questions about regions, and so what future work that we're intending to look at, because in these scenarios, we didn't look at the expansion of storage beyond what's planned in the WEC process out to 2050. Obviously, that is highly uncertain, especially given the declines in the cost of battery storage in particular that's been experienced in the last couple of years. That also relates to how much solar might be deployed as well. Just to get everyone grounded on this analysis, we are looking at transmission and curtailment in the wind vision scenario, which, as Jenny explained earlier, has 37% wind available energy by 2050, and in the geographic distributions close to what is shown on the map that you see here. So one of our findings was that the generator flexibility and perhaps storage in relation to that might not have a strong impact on reducing curtailment. Now, that is only assuming the distributions and level of wind versus solar that one sees here. Going forward, what we want to look at is how storage might impact that story and how the distribution of wind might be altered, as well as the levels of wind versus solar might also differ given a different kind of storage future. That's all ongoing work. We don't know the exact specifics of that yet. It could include other regions beyond the West, as was asked by a prior questioner. As well, I would mention we do have ongoing work looking at transmission expansion between the interconnections and between countries with the U.S. and Canada and Mexico as well. So stay tuned for all of that exciting work, but happy to explore more questions here specific to this analysis.
Great, thanks, True. I'm going to lob Jenny a softball before we get back into the more details, some of the more detailed questions here. What was the gas price forecast that we used for this this analysis?
We used the gas prices that came from the Wind Vision study for 2050, which was $6.8 per MMBTU. So remember, that's 2050, so that's a long time from now. And also we did our sensitivity with plus or minus 25%, so that's somewhere between like $5 and $8 for MMBTU, including those sensitivities.
Great, thanks, Jenny. And True, I think maybe this next bundle of questions heads to you, as I think this was somewhat addressed in the overall Wind Vision study. There's a couple questions about the cost-benefit analysis and whether this analysis will we will extend this analysis to include the cost-benefit of the capital cost of the renewable generation, and I think this is relevant to the overall Wind Vision study. And also a subsequent question that's related is, what was the basis for the wind to solar ratio that was close to a multiplier of 3 in the Western Interconnection?
Sure. So on the cost-benefit question, the Wind Vision study did look at transmission expansion in a slightly different way using a different modeling framework, but as Jenny mentioned, with some of the similar conclusions here. So the economic cost-benefit assessment is embedded in that NREL REITs model that I mentioned earlier, which has all of those elements rolled in together, including all capital and operating costs for the full electric system, again, on the generation and the transmission side. So if you refer to that document, you'll see some of the analysis there, which does highlight that the potential for wind to be economic, or more specifically, the Wind Vision scenario to be economic, inclusive of transmission in the long run, but in the nearer term, there may be some additional support that would be needed to make that economic case. On top of that, the Wind Vision analysis, as I mentioned in the very beginning, included some other non-direct electric system benefits and impacts related to air pollution and health impacts related to greenhouse gas emissions, natural gas consumers and producers, as well as workforce requirements and water use from the electric sector. So certainly refer to that document for a more complete assessment there. On the question of wind versus solar, that's a direct result from how the Wind Vision scenario was constructed out of the NREL REITs model and as part of that study. Just to highlight that for that particular Wind Vision study, we had the target of 20% by 2030 and 35% by 2050 wind penetration, and allowed the model under the assumptions used to build the remaining system, which in this case, resulted in 12% solar. That being said, we have also done other analyses and other scenarios that looked at different mixes of wind and solar. I think the question about whether or not from a curtailment perspective what the optimal mix is still uncertain, but that does have to roll in the factors of storage and other components that you see there. So we do have a related analysis. I'm happy to follow up with more specifics. But for this particular scenario and analysis that we presented on today, it is closely tied to the work that we did for the wind vision study in 2015. So the kind of assumptions are largely based on that.
Okay, great. Thanks, Drew. And then a somewhat related question is how sensitive are the conclusions that we've made in this study to the mix of wind and solar? And Jenny, I'll take that one if you don't mind.
Okay.
So, we've done a lot of work here at NREL looking at a variety of scenarios. In this work, we really focused on a single portfolio, but we've definitely done a number of studies looking at multiple different portfolios, and some of the conclusions from that work will likely hold true for this work. And most of what we found, the study that pops first into my head for the Western interconnection is phase 2 of the Western Wind and Solar Integration Study, where we had a high wind scenario, which was 25% wind and 8% solar, a high solar scenario, which was the opposite, 25% solar and 8% wind, and then one that was an even mix of wind and solar to make the 33%. And what we usually find in these studies is that a good mix of wind and solar makes operation of the system the easiest. I won't particularly comment on capital cost here because Drew commented on that for the Reed's work. But in terms of system operation, a mixture of wind and solar and any kind of diversity, especially between technologies, tends to be the best for system operations. Curtailment was substantially lower in phase 2 of the Western Wind and Solar Integration Study in the even mixture of wind and solar. So I think it's safe to say that operations would be as easy or easier if we start looking at more even mixtures. If you start heading more towards a heavy mixture of solar versus wind, or basically a swapping of this particular scenario, you might start looking at different types of challenges. Maybe less challenges on the transmission side of things, but more challenges on the operational side of things. I'm sure most people on this call are familiar with the duck curve. As we reach high levels of penetration of solar photovoltaics, all solar PV in a geographic region like this is highly correlated. As you end up with solar noon across the West, maybe varies by an hour or so, and so even transmission across the West only helps a little bit in spreading some of that. The timing of the solar generation, and what you end up with is a lot of energy at noon and not as much energy at sunset, and so you have to have resources available to cover that. And so when it comes to different mixtures of wind and solar, yeah, I mean I think we expect to see certainly we expect to see different conclusions, with it likely getting easier the more diverse the portfolio is, and potentially getting more challenging in different ways as high penetrations of solar might come around. Next question, there was, and this is somewhat related, how important do you feel that fast generation or quick responding generation and or load response is to balancing the variation in renewable generation? Jenny, do you want to take a swing at that?
Sure. So, I mean, I guess our analysis gets at this a little bit. If you remember, we had a sensitivity where we eliminated all coal generation from our portfolio, meaning that what we were left with was gas, combustion turbines, and combined cycles, which we typically think of as faster response, quicker to ramp. You can turn them on faster and that kind of thing. And as you can see, or as you saw in that scenario, we only saw curtailment decrease marginally. So usually what we observe is that, with all the generators on the system, there is enough flexibility from the generator fleet as a whole. And so even getting rid of those inflexible generators doesn't always help you all that much. Of course, we did see a small benefit from it, but nothing huge.
Yeah, and I think it's important to caveat that with the fact that, the scenario we ran that one on was a heavily transmission constrained scenario, so some of the generation was stuck in Montana and Wyoming, and the penetration levels might not have been quite as high in the rest of the Western interconnection. And this is a little bit related to another question about how conclusive is the finding that that flexibility is through transmission is the relative importance of that to storage or demand response or quick responding generation. And I think it depends a little bit on the scenario you're looking at. For this big scenario where we've got the entire Western interconnection to respond, then the quickness of the response of the generators is maybe not as important, because we've got so much diversity in terms of the renewable generation, in terms of the ability of generators to respond. There's basically, all that diversity reduces the variability in general, and all that diversity in non-renewable supply makes it easier to respond to the variability. If you start looking at smaller regions and how specific utilities might start responding to some of these things, if they don't have the ability to use transmission to access all that diversity, that's when I think some of these other things like quick responding generation and things like that might become really important. And I think it's also fair to say from other work that we've done that the higher penetration of renewables you start looking at, and the more constrained your system is, the more important it is to have sort of every solution available in your toolbox. So having load response and things like that, certainly in certain scenarios could be really important. So we've got just 3 minutes left here. Let me see if there's another question. Sorry, we're going to end up missing a couple of these. There's a couple long ones. Jenny, did you want? Is it possible to comment real quick? You have a backup slide on emissions, and there were a couple of questions about that that showed the emissions between the different scenarios. And what we saw, I believe, was as you start adding transmission, carbon emissions go down and go down and go down. So that's the 4th column there, the CO2 savings compared to the reference. But then when you look at the copper sheet, they go back up. Do you believe that's because the first few transmission scenarios are allowing us to send the renewables to the load and reducing curtailment? And as we reduce curtailment, we reduce carbon emissions, and then the carbon emissions come back up in the copper sheet scenario because we can tap into all the coal generation throughout the West, and we basically never have to run gas generation. Is that fair? Okay. I just wanted to make sure that my thoughts on that question coincide with yours.
Yeah, but even the copper sheet, it does show substantially lower CO2 emissions than the reference scenario, and that is due to curtailment, like Greg mentioned. So all of our sensitivities to that did show reduced CO2 emissions. So.
Okay, great. So we're just about out of time here. I think we definitely want to thank everyone for listening today, and please feel free to contact us with follow-up questions. We'll be posting the slides and the recording of this webinar if you're interested in sharing it with colleagues or anything like that. True, am I missing anything here?
No, I think you got it covered.
Okay, well, great. Thanks, everyone, for listening. We appreciate it, and we'll have more of these webinar series. I'm not sure which one's next, but in the next month or two, I'm sure you'll be getting an email with our next segment of the webinar series. Thanks, everybody.